Hello students, welcome to this lecture. In last few lectures we have been discussing the Hartree-Fock theory. We have seen how we could obtain the Hartree-Fock equations and Hartree-Fock energy, what are its interpretation. We will continue our discussion along that line. If you recall that we have formulated the Hartree-Fock problem in terms of the spin orbitals. Essentially what we said is that by solving these one electron Fock operators, we are getting this a set of spin orbitals which are orthonormal. So these spin orbitals have their one electron wave function with a definite spatial identity and spin identity. So if we want to express this spin orbital in terms of the spatial orbital, we have already learned how to do it. We essentially have to take care of the spin integration. So here the spin orbital chi I, whose coordinate is given as x, depends on can have either we have psi j as the spatial orbital with an alpha omega spin, or psi j as the same spatial orbital with beta spin. So this indicates that I can have two different spin orbitals starting from the same spatial orbital psi j, one with an up spin, another with a down spin. So here the r is the coordinate of the electron, the spatial coordinate of the electron, omega is its spin, and x is the total coordination to taking care of both spatial and spin. So therefore we have got from n number of spatial orbitals, we can construct 2n number of spin orbitals. That this is what we have seen. Now what we do is that we will discuss some commonly occurring notations in quantum chemistry. One thing is this, the so called closed shell and open shell. We would see that when, so these are different spin orbitals, so the alpha spin, beta spin. Now what you see is here that I have got two spatial orbitals. Each spatial orbital has two spin orbitals, alpha and beta. So 1 alpha 1 beta, 2 alpha 2 beta. So I see both the spatial orbitals are doubly occupied. When all the spatial orbitals of a system are doubly occupied, that means they hold one up electron and another down electron, those systems I call them as closed shell system. So overall spin multiplicity is singlet. Now on the other hand, I can have this open shell configuration where one or more number of spatial orbitals are singly occupied. So in this case I see one unpaired electron, so therefore it has a doublet spin multiplicity. I also can have triplet or higher spin multiplicities, and I will call them as open shell. So essentially the closed shell systems are those where all the spatial orbitals are doubly occupied. Now within closed shell we can formulate our problem in two different ways. One we call restricted, another is unrestricted. The difference between restricted and unrestricted is how we are treating the special function for two electrons. Suppose I have got in this case I have got the same spatial orbital 1 alpha 1 beta. In the restricted formalism, what I say is that this alpha electron and beta electron, they have exactly same spatial function. Similarly 2 alpha and 2 beta, I say that these two electrons have exactly identical spatial function. So in those cases where I am treating the same spatial function for spin up and spin down electron, I call them as restricted. So I am putting a restriction that the spatial part of the wave functions are identical. But in many cases it so happens that for a proper description of the molecular wave function, we need to distinguish the spatial part of the up spin electron and down spin electron. So I am showing this in case of unrestricted closed shell system. So where the alpha spin and beta alpha electron and beta electron noted by the up sign and down sign are taking two different form of spatial wave function, the one signifying the blue and the orange spatial function. So, now two electrons spin up and spin down, they take up two different spatial functions, and in that case we call unrestricted system, unrestricted representation. Now, this was about the in case of closed shell. I can do this, discuss the same in case of open shell, where as we discussed in open shell, at least one or more spatial orbitals are singly occupied. In this case, for an open shell system, if I consider restricted representation, that means both spin up and spin down electron are having same spatial function. On the other hand, in case of unrestricted, I am using different spatial function for the spin up and spin down electron. So, now you can actually in case of the open shell system, you can realize that overall interaction pattern, since there are different number of upspin electrons compared to the downspin electron. So, therefore, the overall interactions are going to be very different from the alpha electrons or the beta electrons. We have seen that electrons with parallel spin have different exchange interaction compared to electrons with opposite spin. So, therefore, in particular in case of open shell system, sometimes it becomes very important to do this unrestricted representation. However, in our present discussion, we will restrict our discussion to closed shell restricted formalism. So, just to remind you, the closed shells are where all spatial orbitals are doubly occupied, the restricted spin orbitals where we have defining same spatial function for spin up and spin down, and when we define different spatial function for the spin up and spin down electrons, we call those spin orbitals as unrestricted spin orbitals. Okay. Now, as I said, we will restrict ourselves to closed shell systems with restricted spin orbitals. Now, in such case, the n electron determinant wave function that I wrote down for in terms of the spin orbitals going from chi 1, chi 2 till chi n, because I have got n number of electrons. So, to represent this Slater determinant, I am using n number of spin orbitals. Instead of that, I can express the same Slater determinant as the spatial orbital, the psi 1 bar indicating the beta spin, psi 2 bar, and it goes from psi n to psi n by 2 and psi n by 2 bar. So, here you see that I am using the same spatial part of the orbital. So, that is why I am calling psi n by 2 and psi n by 2, that means their spatial functions are same. It is only the spin functions that are different, one is alpha, another is beta. So, I already have seen earlier how in this case I can take out the spin part and do spin integration separately and rewrite the expression in terms of spatial orbital. If you go back a few lectures earlier, you would find out that we had actually obtained this determinantal energy for any Slater determinant phi with Hamiltonian operator, which has one electron operator and 2 electron operators. We obtained the determinantal energy in case of spin orbitals as this one, and in case of spatial orbital we obtained the determinantal energy in this form. Note the difference, in case of spin orbitals I use angular brackets, in case of spatial orbital I use round brackets. In addition, I have the summation is over all spatial orbitals, because now I have got only n by 2 spatial orbitals, but n number of electrons. So, therefore, I have got in the one electron the core energy, I have sum of n by 2 terms, but multiplied by 2, and in case of the Coulomb band exchange I have got n by 2 spatial orbitals. Here I have got Coulomb term twice, exchange term 1, that is because we see that electrons with parallel spin can contribute to Coulomb term and exchange term, whereas electrons with opposite spin contribute only to the Coulomb term. So, therefore, the Coulomb terms get twice as many interactions. So, these are the, now if I express this phi, if my Slater determinant phi is the Hartree-Fock wave function, this energy is my Hartree-Fock energy. Now, since while we are solving the Hartree-Fock problem, we essentially solve the Fock operator, the differential equation corresponding to the Fock operator. So, it is, let us write down the Fock operator in terms of spin orbitals. So, this we have already seen, Fock operator corresponding to one electron has its 1 electron term, the core Hamiltonian, plus the exchange, the Coulomb band exchange. So, these are the effective 1 electron operators, where we see that the Coulomb and exchange operator, they explicitly depend on 1 electron, because we are integrating out the coordinates of with respect to all other electrons. So, all other electrons are being described as a charged cloud which is interacting with the electron I. So, therefore, these operators J and K, they have dependence, explicit dependence on only on electron I. So, this summation shows that I am taking care of all other all other spin orbitals. Now, when I convert that to special orbital language, I would have the same Fock operator corresponding to electron I have this core energy, plus now I see that the sum goes from instead of n, it goes to n by 2, because I have those many special orbitals, and I have, for the same reason that we discussed, we have twice the Coulomb operator minus exchange operator. So, this is the Fock operator in special orbitals. You can in fact rederive this exactly following the way that we did while we took care of the spin integration in a few classes earlier. So, you can write down the Fock operators expression in terms of spin orbitals and do the spin integration, and then you would come to this form of special orbital Fock operator in terms of special orbitals. Now, in special orbital, let us look see how these Coulomb and exchange operators are defined. So, Coulomb operator JBI, when it acts on a special orbital psi a, I get the following expression. So, here psi ai, this Coulomb operator works as an eigenvalue problem. So, here you see the psi ai is reproduced over here. Now, what you see here in the integral are some terms which depend on j electron. So, psi b star j, psi b j, together they describe the probability distribution of electron j occupying spin orbital b, special orbital b in this case, and I have this term 1 over Rij. So, when I integrate this term out, the j coordinates are taken care. So, therefore, as a result, since the operator depends also on electron I, so this term depends on coordinates of electron 1. So, therefore, this is an operator depending on electron I. Now, this is how the Coulomb operator is defined. In case of exchange operator, I have exchange operator when it acts on the special orbital psi ai, it would have exactly the similar form that we had for the spin orbitals. So, we know that when exchange operator acts on psi a or special orbital, it would exchange the electron from electron I, instead of occupying psi a, it occupies psi b. So, this is not an eigenvalue equation. So, psi ai goes to psi bi. Now, the rest of the part which depends on electron j is psi b star j on the left hand side, psi a j in the right hand side. So, therefore, there is no probabilistic interpretation here, there is no classical description like we had in the Coulomb term. So, this is my exchange operator. So, we will see how the exchange operator and Coulomb operator act on the special orbitals. Now, since we know now how Coulomb and special orbital, Coulomb and exchange orbital operators act on special orbital. So, therefore, we can rewrite this Hartree-Fock equation with the special orbitals, where this is the Fock operator defined in terms of special orbitals. We have to keep this in mind, because these are very special operators. Fock operator, which is sum of the 1 electron term and the Coulomb and exchange, all these operators actually depend on their the orbitals with whose solution they want to provide. So, therefore, the operators themselves have been would change their form, as we have seen here. So, this is very important to keep in mind, that how the operator is defined. So, this Fock operator, when it is defined in terms of the special orbitals, it will follow this eigenvalue equation, where epsilon a is now the orbital energy corresponding to the special orbital psi a. Now, let us try to find out the expression for the energy for special orbital, that is epsilon a. So, we would see now, since we know what is the form of the Fock operator, we can get the expectation value psi ai Fock operator psi ai, that would give me epsilon a. So, you would see the first term I have hi. So, therefore, the first term would be the core energy, I see that the round brackets are over here, so signifying that this A is actually a special orbital. And since the next term is the Coulomb operator JBI, so I would see I simply have to multiply psi A star and integrate this function psi A star to the Coulomb term over here and integrate that term. So in that case I would get 2 times AB, that is the Coulomb term, and similarly I will get an exchange term. In other words, I can write down this HAA, the core energy, the Coulomb energy and the exchange energy. So this is the expression for the energy for a special orbital A. Now the Hartree-Fock energy we have already seen in the previous slide. I am just writing them down again. So I have twice this core energy plus the Coulomb and exchange energy. Please note the similarity in the Hartree-Fock energy and the orbital energy. Now what we would do is that we would take one example electron configuration and try to find out its Hartree-Fock energy and its orbital energy. Suppose this is the situation. I have got 2 special orbitals 1 and 2. So each special orbital can occupy 2 electrons. So I am considering this electronic configuration where I have 2 electrons in the special orbital 1. What would be the Hartree-Fock energy? The Hartree-Fock energy is given here. So I would get 2 HAA. So that means 2 H11, because I see that 2 electrons are occupying special orbital 1. Each electron occupying special orbital 1 will contribute to the core energy as H11. So since there are 2 of such, so there I will get 2 H11 plus what are A and B? A and B are the special orbitals. Since I have only one special orbital which is being occupied here, so this sum here A and B are simply 1. So therefore I would get the second term will be 2J11 minus K11. But you would see that, so this is the term I get, twice H11 plus 2J11 minus K11. Now this expression what we see over here, look, J11 and K11 can be shown as identical. You can see here J11 means I have psi 1 the special orbital in the bra, psi 1 in the special orbital in the ket, and I have the JB operator, and similarly for the exchange. Since both the orbitals are both the electrons are occupying the same orbitals, so therefore the J11 term and K11 term will cancel out. So therefore from 2 times J11 minus 1 K11 will give me 1 J11. So this would be my Hartree-Fock energy. If you remember a few classes earlier, we discussed classical or pseudo classical way of finding out the energy of a particular conformation electron configuration. So this is what we would have got in those cases. We would have seen that 2 times core energy plus 1 time Coulomb interaction. There is no exchange interaction because the 2 electrons are of opposite spin. So this is what we had known, and this is what we are getting over here. Now what about the orbital energy? To get orbital energy, we already know the orbital energy is essentially the energy that an electron experiences in that particular orbital, because we discussed in the previous class how orbital energy is related to its ionization potential. Now if I want to write down the orbital energy epsilon 1, I would say consider this electron. What is its energy? What is its energy when this electron is present over here? So anyway, orbital energy expression is written down here. The first term is HAA. So I am considering one electron now, H11. Then the second term is 2J11 minus K11, because in both cases A and B are 1 anyway. So therefore the second case I said 2J11 minus K11, and I have already seen J11 is equal to K11. So that gives me H11 plus J11. What is the difference? The difference is that when I am looking at this orbital energy, I am only considering the energy of one electron. What is that energy of that one electron? That is H11, its core energy, plus its interaction energy with the other electron. Now if I had considered the other electron also, that would also have given me same value, because both the electrons are occupying now the same orbital. So this epsilon 1 is actually the orbital energy. orbital energy is defined by looking at the energy that one electron in that orbital experiences while it is in that orbital. So, in this way we can see that when we can write down a particular electron configuration, we can find out its orbital energy, its Hartree-Fock energy. Of course, we are expressing them in terms of the some standard integrals h11 or j11. Their absolute values are something that we need to calculate. Most of the times we would do that using a computer, but we can interpret the result in this way. All right. Now what happened is that we have expressed our Fock operators in spatial orbital. This is the one, and we can write down the corresponding Hartree-Fock canonical equation when the orbitals are expressed as spatial orbital. Now while solving this, these Fock operators represent integro differential operators. So I have to solve these problems. While I can solve these problems numerically using a computer, but when I go to larger and larger system, the efficiency becomes better if I use another approach, and this idea or this approach was given by Roothan. So that is why what we are trying to do is now introducing Hartree-Fock formalism with another idea that was given by Roothan, and we will call together this formalism together as Hartree-Fock-Roothan scheme. Now what is the idea of Roothan? Roothan suggested that now to solve this integral or differential equation, it is not very efficient numerically. So if we can convert this problem to a matrix formulation, then we can use matrix algebra and matrix diagonalization techniques and can easily go to larger systems with very little additional programming or additional effort, except for requiring more computational power. Now what Roothan suggested is that let us see this, we have got this psi a, the spatial orbitals. Now let us start calling these spatial orbitals as molecular orbitals or atomic orbitals if the system is an atom. So these molecular orbitals, we can define them or we can describe them as a linear combination of some standard basis function. So what he suggested, Roothan's idea was to introduce a basis. So he introduces this basis, let us call them theta nu, where nu goes from 1 to k. Ideally, this basis to be called a complete set, we should have infinite number of such functions. But practically speaking, this is we can never find infinite number of functions. What we will do is that we will find a large set of functions which will span a space, and within that space this basis will work as a complete set. So since this basis works as a complete set within the space that it spans, we can express an arbitrary function. In this case, the arbitrary function is the spatial orbital or the molecular orbital. We can express this molecular orbital as a linear combination of these basis functions thetas with this coefficient c's. So I am expanding this in terms of theta nu. So therefore I have this coefficient as c nu a, and I can write this for a goes from 1 to k. So if we are taking k number of basis functions, from this linear combination we can construct k number of molecular orbitals psi a's. Alright. So now what we will do is that we will put this information into this Hartree-Fock equation that we have written down. So here I have the Fock operator acting on the molecular orbital, giving me the molecular orbital energy and the orbital. Now wherever I have this molecular orbital psi a, I would replace that with this basis expansion. So let us do this. In the left hand side I have the term. So here I am expressed, instead of psi a, I have written down c nu a theta nu, and the right hand side I have done the same thing. Now what I am doing is that I am multiplying this theta mu star from left hand side and integrating the equations both in the left hand side as well as on the right hand side. So the terms written in the red are introduced in this line. So when you look at this, I would see that I have got this some summation terms plus these coefficients. I should bring them out both in the left hand side and in the right hand side. This is what I did. I removed this summation term and brought them out. So, I essentially have these integrals integrations to be done within this summation sign, and similarly in the right hand side. Now, let us look at the terms carefully. What is this integration tells? This is simply a matrix element of this Fock operator, where the bra is theta star mu, the bra is theta mu, the ket is theta nu. So, this is essentially the matrix element of Fock operator, mu nu matrix element of Fock operator. And similarly, when you look at the right hand side, you would see this is nothing but the overlap of two basis functions. So, this theta mu and theta nu are something that I know. I would start from with a known set of basis functions. We will come to that what can constitute a good choice for known set of basis functions, but suppose whatever choice we made, these overlap functions and these matrix elements we have to evaluate. So, now what we are writing, I am writing down is that instead of writing this term, I am writing this it as matrix element. So, this matrix element I am calling as F mu nu multiplied by this coefficient C nu A. Then in the right hand side, I have the overlap matrix S mu nu and the coefficient C nu A. So, here this equation I can obtain for n number of times, k number of times, because for each value of A, I have one equation like this. Why this k is coming? Because I have expressed now psi A as a linear combination of k number of known functions. So, you can see, since I have k such equations, it is it would be convenient if I can convert it to a matrix form. So, in matrix form, this would look like this: Fc equals SCE. The E would be the energy term. So, this epsilon S that are coming. S is the overlap matrix, C is this coefficient matrix, F is the Fock matrix. Now, either I have this matrix formulation, or the way we discuss the linear variational principle, or even the perturbation theory, that time we had to solve this secular equation, where we have to find the roots of this determinant F minus ES. So, whether we express it as a when we express it as a matrix. So, this is how the Fock matrix or the overlap matrix would look like. So, here I have the basis functions theta 1 to theta k, theta 1 to theta k. So, I would have this matrix element F11, F12, F1k, and these are the diagonal matrix elements. So, the moment I choose a set of basis function theta nu, I would immediately be able to construct this Fock matrix. Now, similarly, I would also be able to construct this overlap matrix. So, S11, SKK. So, these, if the starting functions are orthonormal, so in that case it will become diagonal, elements will be 1, after diagonal elements will be 0. If they are not orthogonal, only normalized, I would have some finite value of the overlap function. So, notwithstanding what exactly is the form of this the basis set that we are using, we can always construct this overlap matrix. So, now we have this Fock matrix, we have this overlap matrix. So, the solution becomes like we have to get this F minus ES, and then we will have to find the roots. Since the matrices are of k by k, I would find k number of roots, because this I will get a set of equations with the order e to the power k. Of the order k. So, therefore, I will get k number of energy solution. Now, this energy matrix would actually be a diagonal matrix with the diagonal elements as the energy of the first k spin first k molecular orbitals, not spin orbitals. So, this eigenvalue, this when I construct them in the matrix and diagonalize this matrix, the eigenvalues will be given from epsilon 1 to epsilon k. They would represent the molecular orbital energy. Now, corresponding to epsilon a, or the eigenvalue 1, I would get one eigenvector, and those eigenvectors would come from this eigenvector matrix or the coefficient matrix C. So, I would have C11 to C1k, and so corresponding to each solution, each eigenvalue, I will have a set of eigenvectors, and these eigenvectors, these coefficients are necessary to do what? They would actually help me in constructing the molecular orbital, because from Roothan's scheme, what has happened is that I am expressing my molecular orbital, which is the ultimate solution, as linear combination of some known basis functions, where the only unknowns are these coefficients. Now, this matrix formulation, thanks to Roothan, now gives us with very little effort the coefficient matrix. Simply it requires formulation of the matrices and diagonalization of this matrix to get the eigenvalues and the eigenvector. The eigenvalues are essentially the energies of the orbitals, molecular orbitals, and these coefficients will be used to construct the molecular orbitals as shown here. So, the Hartree-Fock formalism that we discussed in last few classes, when you couple that with the Roothan's idea or the matrix formulation of this Hartree-Fock scheme, we get this beautiful Hartree-Fock-Roothan scheme, and this scheme is now ideally suited for use in computers, so where we can simply diagonalize extremely large million by million matrices without much effort. So, in that context, with the rapid growth in our computational power, the Hartree-Fock-Roothan scheme is what we normally use in standard quantum chemical calculations. So far in this lecture, we have looked at the growth of Hartree-Fock formulation starting from Fock's contribution, then starting from Hartree's idea of self-consistent, followed by the contribution of Slater and Fock, and now we see that how Hartree-Fock formalism can be coupled with Roothan's idea of introducing a basis and thereby making it widely applicable to large molecular systems. Thank you for your attention.